walk faster. However, I'm going to have a review of vectors. Do you hear me?
I do.
Yes, okay. Now, in this lesson, I will explain the meaning of equal, opposite, and different vectors, because many students are confused when they are dealing with equal, opposite, or different vectors. That they are not able to make distinction between these three concepts. How to add and subtract two or more vectors in a straight line first. Then I'm going to explain the two rules of vectors addition when they are not in a straight line. And then I'm going to explain the difference of vectors as the sum with the inverse, because the difference of vectors means if we subtract two vectors, but we are going to express it as a sum of vectors, not as a difference. And the last thing that we are going to review today is to add or subtract vectors using coordinates. This is much important for physics. So here it is a short introduction. In the article in the topic vectors and scalars in physics, we have discussed about the properties of vectors such as module or magnitude, we said, components, the x and y components, direction. The direction was determined by the angle of the vector to the horizontal direction. So if we say a vector that is 45 degrees to the horizontal direction, that means we are showing the direction of the vector. It is not only the line, but also it is important the angle with the horizontal direction, and the respective trigonometric functions stemming from it. We saw the cosine of the angle theta, the sine, the tangent, cotangent, and so on. However, the discussion was concentrated only about a single vector quantity. But what happens when two or more vector quantities act together in the same object or system? For example, if two or more people pull the same object, if two or more displacements are combined together, etc. You will know the answer after reading this article. So now I will start with the distinction, with the explanation of equal, opposite, and different vectors. Now, by definition, if two vectors are equal, when the two vectors are equal when they have both the same magnitude, the same size, that means, and the same direction, when they are parallel. Look at the figure. In this figure here, we have the vector A and the vector B. They are equal because they have the same length and they are directed in the same they are in the same direction. Both are due right, let's say. Here we have two equal vectors A and B. Two vectors are opposite when they have equal magnitude, but they have opposite directions. That means when the first vector is due east, the second vector is due west, but they both have the same length. That is the meaning of opposite vectors. In all the other cases, we have different vectors, neither equal nor opposite. Equal vectors are when they have both magnitude and direction the same. Opposite is when they have the same magnitude but opposite direction. That means when these two vectors form an angle of 180 degrees to each other. If I place the vector B here, we are obtaining two vectors that are in opposite directions, so they have 180 degrees with each other. Equal vectors have an angle 0 degree to each other, and and all the other cases represent different vectors. There are 30 cases in which we have different vectors. When we have two vectors which have different magnitude and different direction, like this, but also when we have two vectors that have the same magnitude, the same length, but they have different direction. Different means neither 0 degree nor 180 degree. All the angles that are neither 0 nor 180 are angles that show different vectors. And the other case is when the vectors are parallel, they have a 0 degree angle between them, but they don't have the same length, the same magnitude. These three cases represent different vectors. Now, I'm going to explain the addition and subtraction of vectors in a straight line because it is the easiest thing to do, the easiest thing before starting with addition and subtraction not in a straight line. The meaning of resultant vector, or maybe you have learned it as the net vector, the same thing. This is the simplest case of the vectors addition in a straight line. For example, if two horses are pulling the same cart, like this one, we have two vectors of forces acting in the same direction. Although the application point is slightly different, because we said that in physics it is important the application point as well, not only the magnitude and direction and the unit. So since these two vectors are parallel, we can place them one after another and obtain the sum of these two vectors. For example, if the first vector is 200 newtons, the second vector is 300 newtons, they show both forces. The resultant vector will be 200 plus 300, it is 500 newtons if we illustrate it with numbers. On the other hand, when two groups of people are playing the rope pulling game, we have again two forces acting in a straight line but in opposite direction, like in this figure here. So again, these two vectors are in a straight line, but they are acting in opposite directions. It is obvious that we must combine the vectors to calculate the overall effect or their sum or difference. This effect is known as a resultant of two or more vectors, or net vector, net force, let's say. Thus, the resultant vector represents either the sum or the difference of two or more vectors acting on the same object or system. The resultant vector is a single vector that virtually replaces the actual vectors. So if we replace both vectors with a single one, but which has the magnitude as the sum of the two vectors, or the difference, as the case may be, we are saying that we have obtained a resultant vector. It is often denoted as V net, not V res, resultant, but often it is known as net vector as well. V is a generalization. We can put, instead of V, we can put F in the case of forces. We can put X in the case of displacement, and etc. Depending on the physical quantity that we are studying. It may represent any vector quantity, the vector V. Now, in the first case, in the figure above, in this one, we have to add the vectors, and in the second case here, we have to subtract them because they are in opposite directions. Therefore, the resultant force it is like we say 10 plus minus 4. We are adding, in fact, we are adding one number with the opposite of the other number if we are going to subtract them. So subtraction is nothing else but it is an addition with the opposite of the second number. And the same is for division. If we are going to divide 24 and 6, it is like if we multiply 24 times 1/6. So division is the inverse of multiplication. We are going to see that we don't need to know the division of vectors because we are going to use the concept of multiplication. Here it is the same as well. We don't need to know the subtraction of vectors, but only the addition, because in the case of subtraction, we invert the direction of the second vector and we do the operation as we have addition. Do you understand? So in this case,
Yes.
instead of writing f right minus f left in this figure, we can write f right plus minus f left, because we are finding the sum of two vectors, but which have opposite directions. Therefore, to avoid confusion, it is better to forget the subtraction of vectors. And whenever there is a situation involving vectors with opposite direction, we must consider it as addition with a negative. Let's see an example here. 3 electrically charged objects are placed in a straight line as shown in the figure. Maybe you remember from the school that the electric charges act with each other with a force that is called electrostatic force, and it is measured by using the equation constant, electrostatic constant K times Q1 times Q2. Q1 and Q2 are the charges in coulombs, divided by distance square. But when it comes the day, we are going to speak again about those concepts. But for now, I'm only remembering to you the concept of like and unlike charges. Maybe you know that when we have two like charges, two positive, let's say, charges, they push each other, they repel each other. But when we have one positive and one negative, so two opposite charges, they attract each other. Do you remember this from the school, or you didn't have learned at school this property of electrical charges?
I have done it.
Okay, so my example is about electric charges that are acting with electric forces, but we are going to determine the direction of forces here. The magnitude of electric forces acting on the second object are F12, that means the force by which the object 1 acts on the object 2 is 24 newtons, and F32, that means the force that the third object acts on the object 2, it is 45 newtons. We have to calculate the resultant force acting on the object 2. So we are going to concentrate only on the object 2. What happens with that? Considering the rule, like charges repel each other while unlike charges attract each other. Let's see the solution. The magnitudes of electric forces acting on the second object are 24 and 45. So we have to, given the above mentioned rule that like charges repel each other and unlike charges attract each other, we have this figure, because this is positive and negative. What happens with the object 1? It attracts the object 2. So the arrow, the vector, must be in this way. But what happens with the object 3 to the object 2? It pushes it. So again, the vector must be on the left. So we have to find the resultant force acting on the object 2. We are seeing here that we have two vectors at the same direction. So both act on the object 2 due left. It is as we push them from this side, but in fact we are going to attract, to pull it from here, but it is the same as I bring it here and there are two pushing forces, the same thing. So basically we must add these forces, 40, 24 and 45, and the resultant vector will be 69 newtons. Okay, it is clear the direction of the net force will be due left because since the both vectors are directed due left, the resultant force will be due left as well. Now let's see the addition and subtraction of vectors that are not in a straight line, are not linear. When vectors do not lie in the same line, it becomes more difficult to find the resultant vector. However, we can use the concept of components so to split the vector into the two main or two basic directions according to the horizontal and the vertical direction. That means obtaining the components as we saw in the previous topic. To ease the calculation of the magnitude and direction of the resultant vector. But first, we must know the two techniques used to draw the resultant vector. They are the triangle rule, or as it is known as tip to tail rule. Basically, this rule consists on placing the tail of the second vector. Tail means the beginning of the second vector, to the tip or to the arrow or to the end of the first one. So the second vector is carried in parallel, is brought here where the first vector ends, and then we obtain the sum by considering a new vector that closes the triangle that starts from the beginning of the first to the end of the second. This is the sum, a plus b. If we have the vector a and the vector b, we are going to place the vector b where the vector a ends, and then we are going to take the resultant vector that starts from the beginning of the first and ends to the end of the second. This is the vector c, that is a plus b. This is the triangle rule basically. And if we have the difference of two vectors, we have to find the difference. The only thing to do is to invert the second vector and to obtain minus b first, then placing minus b where the first vector ends, here is the vector a, here it is minus b, and then this new vector is the difference, a minus b. This is the triangle rule. The parallelogram rule, or as it is known as tail-to-tail rule, we bring both vectors at the same origin, at the same place. Then we build a parallelogram that is based on these two vectors, and the diagonal of the parallelogram is the sum of the vectors a plus b. The vector a is this one, the vector b is this one. They have the same origin together. We form a parallelogram. So we take parallel lines here to close the parallelogram, and the vector that starts from the beginning of the two vectors and ends to the opposite angle or to the opposite side of the parallelogram, it is the sum, a plus b. About the difference, we again invert the second vector, invert from the arrow on the right, we get the arrow on the left. Then the second step is to bring them with the same origin. A is here, A doesn't change direction, only B changed direction. So the vector minus B is brought here, and we form again a parallelogram and we obtain the diagonal. maybe you can see that we have the same parallelogram here and here, and in the case of the sum, the longer diagonal represents the sum and the shorter diagonal represents the difference. If we have two vectors that has formed that parallelogram. So we can use two conclusions from all the above figures. The vector sum a plus b, c is the vector sum a plus b is the same in both methods. Whatever method we use, either the triangle method here or the parallelogram method, we have the same vector. So whatever method we use, we obtain the same result. If the second conclusion is if the vector sum gives the diagonal of the parallelogram formed by the two vectors and their parallel extensions, the vector difference gives the other diagonal of the same parallelogram, as we said before. I'm trying to complete two topics at once because they are easy. I'm walking faster than usual. If you don't understand, please you can interrupt me and asking questions. Addition and subtraction of vectors in coordinates. This is very important in physics. As we discussed in the previous article or topic, a vector can be projected on two or even three, if we are in space, a dimensional system of coordinates. If we denote the vector AB, the vector, our vector, if we then denote as AB, where A is the tail and B is the tip position, it is obvious we have two pairs of coordinates representing the vector AB. Two coordinates, one x and one y, are for the point A, and one x and y, another y are for the point B. So we have four coordinates in total. Therefore, the equation for the horizontal and vertical shift of the tip in respect to the tail are, as it is here. Here we have x of A is 1, x of B is 4, y of A is 2, y of B is 4. If we want to obtain the shift in the horizontal position, we must subtract the x coordinate of B and the x coordinate of A. 4 minus 1 here, it is 3. So the point B is shifted 3 units on the right of the vector A, we say. And about the vertical shift, we get the y coordinates of vector B and vector A, and we subtract them to obtain the vertical shift. So 4 minus 2, it is 2. The y coordinate of our vector, because we don't get 4 coordinates to express a vector, but only 2 coordinates that show the shift of the tip compared to the tail. Now, as I said before, delta x, the shift in the x position, is 4 minus 1, it is 3 units, and the shift in the vertical, in the y position, it is 4 minus 2, it is 2 units. Therefore, it would be better is we carry in parallel the vector AB. If we carry it in parallel and bring it here, we don't need anymore the coordinates of the point A because they become 0, 0. And the vector, the point B, is not anymore 4, 4, but it is 3, 2. If we bring it here, the position of the point A will be 0, 0. We don't take any more in consideration, but we take in consideration only the coordinates of the point B. That will be 3, 2. That are the shifts that we found before. This one is the figure. We carry it in parallel and brought the vector here. We are only considering the coordinates of the point B. Here the values 3 and 2 show the components A, B according to the x to the horizontal direction and AB according to the y of the vector AB when its tail is placed at the origin. So we don't need any more 4 coordinates, but only 2. So therefore we can only consider the horizontal and vertical shifts of the tip to the tail, regardless the position where the vector is. In this regard, if we want to add 2 vectors when the coordinates are given, we can simply add mathematically the respective components. So here, if we have to add these 2 vectors, we must add the shift in x of AB, xi plus, yes? So, sorry?
I'm so sorry, my internet tripped off for a bit. Could you please go back a bit?
Okay, again, I was saying that these 2 shifts represent the AB according x, this one, and this one represents AB according y. And they are very helpful if you don't see the vector. But if anybody says to you, can you draw the vector 5, 4 or the vector 3, 2? You say yes, because you know that the value 3 represents the horizontal shift. You can place the origin of the vector to the 0, 0, and the tip of the vector will be to the shown coordinates. To the position 3, 2, you only need to know the coordinates of the point B to the coordinates of the ending point. So you are able to draw this vector without any problem. But if we have more than one vector and we are going to add them as we said before, instead of putting them one after another and applying the triangle rule, or putting them at the same origin and applying the parallelogram rule, if you have the numbers, it is not necessary to use those 2 methods, because you simply use the coordinates and you add the coordinates of the vectors. You add the shift in the x position of the vector AB to the shift of position of the second vector. You add with each other and you obtain the total shift of the 2 vectors in the horizontal direction. The same thing you do with the vertical direction, but in this figure you must take into consideration the fact that the vector AB extends towards negative. It is going down. And if you are going to add the y coordinate of the vector CD with this one, you are not going to add mathematically, but you are going to subtract, because the vector CD is going upwards, the vector AB is going downwards. You are going to take the difference here, and here the sum, because they are moving in the same direction on the right in this case. Let me explain with symbols. So if we are going to add AB plus CD, these 2 vectors, we are going to add the delta AB, that means the x of B minus the x of A, that shows the shift in the vertical position, in the horizontal position of the first vector. And the same thing you are going to do with the second vector, xd minus xc, to obtain delta x of CD, like this one. The same thing you are going to do for the y coordinates. You are going to subtract yb and ya to obtain delta y of the vector AB, the vertical shift. And the other thing is done with the The same thing is done with the second vector as well. I'm going to illustrate you with numbers. Don't worry about that, because here we have a numerical example. You are going to see more in details, and you are going to have mathematical substitution of the numbers. So after doing that, I'm going to do an example. An object moves linearly. Linearly means at the same direction, at the straight line from 0 to this position here, to 714. No, this is from 0 to 6, 8. This is the first vector. Let's see the numbers better. So an object moves linearly from the origin of the coordinate system to the position 7 meters, 14 meters. So from here, it goes here, the object first. Then it comes back in that position, because the problem says that it changed direction and moved linearly for other 1 meter due west. Due west means due left in our case, and 6 meters due south. Due south means downwards. We have 714 at the beginning, that it moves -1, so it goes at 6 in the west-east direction, and in the north-south direction, it moves from north to south 6 units, so 6 meters, so it goes at 6, 8 finally. So the resultant vector will be 6, 8, but we are going to see it with numbers. Here, the solution. Since east is positive, the final horizontal coordinate of the vector will be delta x1 plus delta x2. It is 7 meters plus -1 meters, because the second displacement was due west, but west is negative. So we must take -1. 7 minus 1, it is 6 meters. The horizontal displacement of the entire, the total vector, the resultant vector. And for the vertical coordinate, we have, first we had 14 meters due north. Then we had 6 meters due south.